Yeah, then welcome everyone again to our session on analysis, ready data and data access. We have 6 very nice talks lined up here today. My name is Alexander Jacob from EURAC Research, and I'm here with Katrin Molch.
Yes, hello. Welcome back to this session. I think we'll have a very interesting session in front of us. My name is Katrin Molch. I'm with the German Aerospace Center, DLR. And I guess without further ado, we'll just start the session. Our first speaker is Andrea Siqueira, and she'll talk to us about CEOS analysis-ready data, specification to remove barriers, increase impact, and promote interoperability. Andrea, the floor is yours.
Thank you. So, good afternoon, everyone. My name is Andrea Siqueira, and I am one of the CEOS Land Surface Virtual Constellation co-leads, together with my colleague from the European Commission, Peter Strobel, who is here, and Steve Laban from USGS. My presentation today is about the CEOS ARD and its latest developments. So I would like to begin by taking a look over the last 7 years or so. CEOS LSI VC first started developing the CEOS ARD analysis-ready data concept and a number of specifications back in 2016. Since then, CEOS ARD products are enabling users to get first-hand satellite data that are ready to use for a wide range of applications. And one successful story is the Digital Earth Africa program. This program takes CEOS ARD as an input to generate value-added products for the African continent, providing timeless information on coastlines, water resources, flood risks, and other products as well. So there was a number of motivations behind the big push to create the CEOS specifications, but the main one has been to reach out to the non-expert user community to increase EO data uptake and usability. Systematic and regular provision of CEOS ARD has the potential to reduce the burden of global satellite data users and, as a direct consequence, boost data usage. CEOS ARD products are intended to be flexible, accessible, and suitable for a wide range of users and a wide range of applications, including time series analysis. As I just mentioned, since 2016, CEOS developed the CEOS ARD definition and a number of product family specifications. We call them PFS. The PFSs provide details on what type of corrections the data providers needed to carry out in order to deliver their data as CEOS analysis-ready data for their user community. These specifications, they cover 4 main requirements, and you can see them in the slide. The general metadata, per pixel metadata, radiometric correction, atmospheric correction, and geometric corrections. Parameters within those requirements are used by the data provider to check if a given data set is a CEOS ARD compliant or not. There are 2 levels of CEOS ARD datasets. The threshold level is the minimum level to meet the requirement, and there is the target level, which is a more stringent criteria and require more corrections in the datasets. To be assessed as a CEOS ARD compliant dataset, the data provider must submit a self-assessment of their product against the PFS. And then this then this dataset is also assessed by the CEOS working group calibration validation. Currently, we have several PFSs, and I'm going to be showing them in my next slide. So SEALS developed PFSs for several products. And you can see them in this slide, like we have a surface reflectance, PFS for surface reflectance, for surface temperature, for normalized radar backscatter, polarimetric radar, and so on. And we have two PFSs that are currently under development, which is the LiDAR one and the interferometric radar in SAR. So the latest news for us, and this was endorsed a couple of weeks ago, is that now we have a harmonized SAR PFS. This harmonized product puts us in a single document the 4 endorsed PFSs that we had before. And they are the normalized radar backscatter, polarimetric radar, ocean radar backscatter, and geocoded SLC. And one of the main benefits of having a harmonized product, a harmonized PFS, is the consistency across all SAR specifications, which makes revision and changes much simpler, since it's only one document that has to be updated when a revision is needed, not 4. So there are normalized radar backscatter datasets that are already SEALS ARD compliant. One of them is the Sentinel-1 that Synergize produces for the Digital Earth Africa program. Also, NovaSAR-1 from CSIRO in Australia, and ALOS-2, Pulsar-2 from JAXA in Japan. They are all datasets compliant to ARD, to SEALS ARD. We also have several ongoing NRB self-assessments, including datasets from the European Space Agency, DLR, NASA, ISRO, CONAI, CARI. So the radar community has been very active with the SEALS ARD for SAR. Another development regarding SEALS specifications is the expansion of the current aquatic reflectance to cover ocean waters as well. Initially, this PFS was developed just for land, but SEALS has been discussing the idea of extending this specification to also cover oceans. And this work is being done with experts from around the globe. And the expectation is that by 2024, those experts are going to have a solution or an approach on how to expand the current aquatic reflectance PFS to cover oceans as well. So here we have a list of the SEALS ARD compliant datasets. These datasets have been already assessed, including data provider self-assessment and the WGCV assessment. This list includes datasets from space agencies and from industry as well. As I mentioned before, Synergize is producing normalized rate backscatter from Sentinel-1, and this dataset is SEALS ARD compliant. So if you would like to know more about which datasets are compliant with SEALS ARD, please go to the web page that I'm showing on the right corner in the slide. So this slide shows datasets that agencies are planning to put through the SEALS ARD process and make them SEALS ARD compliant. And you can see that there are lots of them. So the expectation is that the SEALS ARD compliant datasets are just going to keep growing. And more information, again, you can find on the web page. So what's next? Expand the PFSs to other domains, and it is one discussion that SEALS has been this discussion has been going on inside CEOs for quite a while. Even though CEOs ARD started in the land domain, now other virtual constellations are taking the lead to develop other PFSs. And one example of that is the expansion of the aquatic reflectance into, oceanic waters. And this work is in collaboration with, the ocean color radiometry virtual constellation and the ARD oversight group as well. So there are active discussions inside CEOs about how to create new specifications for other domains. And the main driver behind those discussions are, of course, the user needs. Further, CEOs is actively discussing how to make all this data available and interoperable in the cloud. CEOs is also advancing the concept of an interoperability framework. The framework has the potential to facilitate data sharing between the scientific community, governments, international organizations, and so on. And we, CEOs, see CEOs ARD as the first step of this interoperability spectrum. The framework will consider a number of additional interoperability factors, including data formats, terminology, metadata, and so on. And this work is just starting inside CEOs, and it has been led by the CEOs Working Group on Information Systems and Services, WIGS, with the collaboration with the virtual constellations and the ARD oversight group as well. So CEOs has also been working with OGC and ISO to create a formal ARD standard. Standardization of ARD concepts is necessary to achieve broad data uptake, particularly in the commercial sector. Formal standards will allow industry to commit resources towards adapting products and processes to produce analysis-ready data as standard products. This will potentially, hopefully, increase data uptake, particularly by the non-expert user community. CEOs is a co-chair of the OGC ISO standard working group, but also several representatives from the virtual constellations and the oversight group are involved in these discussions. How to get involved? We have been engaging with the broader community through different forums like BiDS', IGERS, Living Planet, JC, VH Roda, and because we consider CEOs, the uptake of the CEOs ARD specifications critical. Any data provider can submit a self-assessment against the CEOs PFS. Any feedback from the data provider during their self-assessment could be used to update the current PFSs. There is the opportunity also for industry to participate in the ARD standards discussions through the OGC ISO working group. And if you are interested, please contact us using the contact, the email in my slide. And through these links, you can find more information about the CEOs ARD, and you can also subscribe to our newsletter and get the latest updates on CEOs ARD. And I think that's my last slide. Thank you very much for your time and attention, and I wish you well with the rest of the conference, and sorry I went over my time. Any questions?
Yes, thank you very much, Andrea. I think we have time for one quick question. Anyone? It must have been very clear. So thank you very much again, Andrea.
Thank you.
Okay, then we welcome our next speaker to the stage, Peter Strobel, who will talk about the proposal of a revised processing level scheme for Earth observation data. Peter, the floor is yours.
Thank you. Yes. The speaker size is not yet harmonized. Good afternoon, everyone. Thanks for joining this session. Analysis-ready data is a topic I think that many people kind of hear up when the phrase is raised. So what I'm going to talk today about is actually an idea of essentially myself that came out of discussions around what is ARD actually, and how do we develop ARD in the future. And when we were starting the analysis-ready data standards working group that you just heard about in Andreas' talk with OGC and now ISO, in the inaugural meeting, I put up this slide because I thought there is one big question yet that is unanswered in ARD, and that's what actually do we really mean by it, and for whom, and how do we basically cut the cake of the data into pieces that make sense to be harmonized and standardized, in the sense that it certainly will be necessary for them to be analysis ready, because we all agree that that means simplification of interfacing, of the way we represent, we format, and we deliver these data to users. So after I was putting that up, I got the honor of a remark of Scott Simmons. Some of you might know him, who is in OGC, knows him, of course, and he said that's the slide of the week. And from that we went into the discussion in the standards working group, and one of the things that came up relatively soon was exactly what is it that we are standardizing here. And that made me think of a talk I had given completely independent of analysis-ready data discussions about a year ago in a relatively small expert circle of hyperspectral imaging experts, thinking about how do we make the future sensors on the US and the EU side, called CHIME on one side and SPG on the other side. How do we make them interoperable, and how do we organize the processing chain so that people can use? And we found fundamental differences in the way we approach that, and that has to do with processing levels. And from that, I was actually starting to think and say, isn't that a more general idea, not just for imaging spectrometers, but for many classes of sensors, that these processing levels, as we have defined them and as we use them as space agencies, and many users refer to them as well, is there maybe something that we can do better? So why do we need them? I think that is relatively clear. Value chains are very long and complex sequences of processes that deserve some structure. We need it. The data change fundamentally from what you receive at the sensor to what actually the end user, if we call them like that, is expecting. So we need to cut that cake into different pieces in order to give it some structure, and in order to develop certain steps that share some commonalities, which makes it easier to describe this data, and ultimately, of course, to harmonize them and to make them what is the ultimate goal, more interoperable. What happened in practice with the initial proposal of processing chains was, of course, everyone jumped on it and started changing it, because it was old, and it was from the 90s, and it was from one player, basically. NASA was the one that was kind of leading the gang there. And not everyone was agreeing to it, so it started to grow pretty wild, and by now I think most of you will agree that it's a pretty heterogeneous picture that you find out there, especially if you go from different classes of sensors and different communities of data users. You will find very different perspectives on them. So why should we reopen the discussion? As said, it's a system that was simply not designed for the purpose of anything like analysis readiness or interoperability as we see it now. That was not a big topic. In the 90s, we were happy when we had two scenes of the same area. So the processing chains also were much simpler at that. The data amounts were much smaller. Pre-processing also was kind of considered something that is somewhere muddled in the ground segments. You don't care about these things, and the users then take over from a certain point, and they have to deal with it. And of course, now we have let's say, a much more elaborate and a much more, but also a much more demanding user community in the sense of how should the data arrive, what should be possible to do with them, and that not only at one but at several levels. So the rest is relatively fast. The CO's processing levels are originally a sequence, as you see here. What we do is, at each level, we do different things at the same time. Usually, we combine refinements on the geometry and on the measurement, as I will call it. Usually, that was radiometry, but we know we have other sensors, so let's call it the measurement. And we could, of course, see these two dimensions separately, because they're not inherently linked. And when we do that, then we have the possibility to open a matrix and to deal with both refinements on separate axes. Here is a proposal, and you're not supposed to read that, and I'm not going to go into all detail, but the main things that I would like to point you at is that we simply have to define classes here that really mean important steps in a value chain. And what I think is what basically everyone will agree is we need a sensor to be calibrated. We need, when we go in remote sensing, that's an important step. If we go from the sensor calibration to what I call the target calibration, we essentially take the effect of the distance, which is the characteristic of remote sensing, we take that out. So we do as if we were at the target. For that, we have to also define what the target is, which is at this stage not necessary. And of course, then we need to go further, because this is a very sensor-specific data set. If we want to bring that together with other data sets, we do what is also here. Terminology is tricky, because these words are not yet really established in a Horizon project. This was called homogenization. And that basically means we take the effect of the sensor out. So we establish a parameter that could be measured by any sensor. It doesn't make really any difference at that point. And then when we go further, we allow much wider, let's say, additions to the data sets which go beyond what was the strict observation. So into any sort of simulation, non-observational data, whatever you want, you can then mix in further down the value chain. Geometry is even easier. There is simply 4 things you need to do with all the data. You need to locate them, then you need to rectify them, because if they are not grids, they are point clouds, and usually that is not something that you can take very long into the value chain, so at some point you have to bring some regularity into it. And then you are basically already at a point where you have to think very, very well about resampling. So you can regrid it once, you can eventually regrid it twice, but you shouldn't do any more, because this will essentially harm your data in a way that if you would be aware of uncertainty, many people unfortunately are not, but then it would become very clear that this is not a good idea. This is what it looks, what we currently have, so we go basically diagonal through that. This is what we could do. And the one thing here that comes back to the original problem where I developed this is something like this. So data which are located, which have a reference, but which are not yet gridded to the ground, is something that in imaging spectroscopy you definitely want to have. These spectra are something that is very difficult to measure correctly, and you want to analyze them before you want to spatially interpolate them. That you can do with the results, like mineral content or whatever. And so that is something you can do by going here to the right and then only down here. And there is many different ways in which you can go through this matrix. And one thing is also very important. For traceability of data processing, you have to encode how your data came to the level at which you are now, because it's very important how and at which stage they were resampled, and this is something that would be relatively easy to code with such a system, even at the per pixel level. Then we can talk about what does that mean for analysis readiness at different levels. Also here, this is, you find it in the paper, this is basically a proposal of what you could call these things. And this brings me to my last slide. So I think we should seriously think about these things. They will help us in defining ARD in a much more concise way than we currently do. We have discussions in the standards working group that go exactly in that direction of, you see that people at different levels have simply different ideas, so we maybe can make that discussion a bit more targeted by saying, let's put it in the right drawer. And then, as I said, traceability, codability of processing change and accommodation of other sensors like remote. Think of the scheme as you saw it. Whatever is at the target calibration level can be measured also in situ. It doesn't have to be a remote, so you can bring the data into the same schemes and you can process them according to the same logic as the others. And with this, I will leave it because I'm slightly over time already.
Great. Thank you very much, Peter. I think those were some very important concepts that you discussed today. I'm sure there's someone who has some questions or comments regarding this. Maybe not in the least the space agencies and data providers who need to change something. Maybe Wolfgang there, please.
Peter, thank you very much. I think it's really important that we have a discussion. I really like your proposal. Say, as a SAR person, I only see a bit of twist that you're leaning towards the optical domain. So I think if we can like evolve a little bit further to better fit those two worlds, it would be really great. But I fully agree with you that we have to distinguish the measurand and physical properties from the geometric properties. That doesn't make sense how we treat it at the moment. Thank you very much.
Thanks. Yes, of course. I mean, this is really meant as a proposal and this is open for discussion. The best place to discuss this right now would actually be really through this ARD-SWIC, because that's where the problem needs to be solved. I don't think we will make any, and we have problems there. We won't make much advance there if we don't get a better grips on what these different product categories are in which we define analysis readiness. And of course, it will be very helpful to have people from the radar domain, because I'm not a radar guy, so if that is still leaning towards radiometry, then my apologies, or optical radiometry, then it should be fixed.
Okay, we have time for at least one other question. If there are not any more questions right now, then I think we can go to the next speaker.
Yeah, maybe one announcement here, because we're talking ARD. I'm not sure STAC was mentioned yet, but it will. We will have sessions afterwards, BOF sessions they're called, 2 of them in a row, talking about STAC and ARD and what this all means. So anyone interested, please join us on that. We need feedback on this stuff. Otherwise, it will be done by very few people, and the fewer people work on this, the less suited usually the results are for the wider community. This is your chance to really get involved in this. Thanks.
Thanks, Peter. Okay.
Okay, so let's move on to the next speaker. Our next speaker is Jan Musial, and he will talk to us about big EO data streaming services provided by the Copernicus Data Space Ecosystem. Jan, the floor is yours.
Okay, thank you very much. Okay, my presentation is here. I am Jan Musial from Cloudflare, and today I will talk about data streaming. We have already some talks before addressing this issue. So regarding the data streaming, now the new Copernicus Data Space Ecosystem has enabled the data streaming. And how is it so? As you know, from 3rd of October, we have replaced the Copernicus Open Access Hub, which we're giving you only the zip files that you have to download and you have to unpack on your site, and then you can access the data. So now there is a huge change in this respect, because now within the CDSE, you have 54 petabytes of data. It's not only Sentinel, so it's also Landsat and other data from several hubs that you had before. Sentinel 1, 2, 3 were on the other hub, Sentinel 5 was on the another hub. Everything now is in one place. Our data in our repository are unzipped, so you are able to access one file. For example, if you just want to look at metadata, you can really download only one data. There is also, all the products are immediately available, so there is no more ordering products, waiting for a storage. All the Sentinel archive is online. And apart from HTTP protocol that was before, you have also now S3 protocol for data access, and this gives you a lot of different opportunities to access the data. Apart from the data, you have also advanced APIs such as Sentinel Hub and OpenEO. We have also a very nice browser now done by Synergize. We have Jupyter Notebook, so this is, allows you to prototype your algorithm using the data. And it's also worth to mention that this is for free, up to some quotas. And if you would like to upscale your application, there is a CreoDias 2.0 platform where you can order some commercial, you can upscale your service with commercial cloud computing capabilities, for example. So going back to data streaming, what is it? We can, looking at Wikipedia, we can find two definitions. First one, it's continuous data streaming, as for example, you have in radio, in TV, and such data should be processed incrementally as they go, without having to access all of data. And this is also a key word, that you don't have to download everything in order to process the data. So the second case, it's more, we will talk about this now. It's data streaming through the internet. So this is a technology to deliver content of devices over the internet. And the thing is that the access to the content should be immediate and also does not have to wait for the data download. So with the first case, I will just briefly go through. This is kind of things that we know. This is GPS, Internet of Things, met stations, smart houses, also satellite downlinks. This is what produces the data constantly, and we are just attaching to the stream. And the second case, it's more, in our case, how it looks like if a user, for example, wants to listen to music or watch video or to process geospatial data, he would use browser or command line interface or some kind of a smartphone app. Then through the internet, he will access the server. And on the server, there is some APIs. For example, I'm sure that you know all of them for media access, but there is also, of course, some other APIs for geospatial data. And on top of that, on the server side, you have on-the-fly processing. So in terms of multimedia, you can have subsetting, you can check different quality of the image, language, subtitles, and on the side of the geoprocessing, you have also subsetting, you have also compression quality, but you have other steps, as was mentioned before, such as reprojection, compositing, resampling, that can be done on the server side. And of course, this API has to access some storage. So then I will tell you a little bit how it works in the CDSE now. So we will start with the source storage, which is based on the open source Ceph technology. Basically, we have more than 12,000 HDD drives in now our storage for this 56 petabytes of data. And if you write, let's say, a Sentinel-2 image in JPEG format, it won't be saved into one drive, because this would be a bottleneck. Basically, the file itself is sharded. It's chunked over a lot of hard drives. So that's why you have a very good performance, because you are downloading the data. If you are going to the storage, it goes through the gateway, which gets the data from different hard drives at the same time. So there is a lot of parallelization here. And with the S3 protocol, you can have more also gateways. So then it allows you for the scalability. And then you have a S3 public endpoint. In our case, this is eodata.dataspace.copernicus.eu, where you can access the data directly using the S3 interface and start streaming data. Or you can use lower level APIs, such as GDAL, Map Server, and GeoServer. And you can also use the higher level APIs, such as Sentinel Hub, OpenEO, that is able to fetch you the data that you require. This is the on-the-fly processing is done here on the server side. So basically, from the user perspective, everything is done in the backend. And this is over internet. And basically what you get, it's the analysis-ready data. The definition, as we know, it's not settled yet, but basically this is resampled, reprojected, also not the entire file, but just a chunk of the file that you need. This is all possible now in the Copernicus Data Space Ecosystem. And one just quick word about the scaling of the system. It's also very scalable in a sense that if you would like to have more drives, you just put more drives, then you put more gateways, and you get more public endpoints. So this allows you to scale the system for next generation of satellites, for example. Also, a very important thing to notice is the cloud optimized formats. So first of all, we have the GeoTIFF, that it's now cloud optimized in a sense that you can access only a part of the file, and you don't have to read an entire file to do this. And what is also important, that it has to be zoomable, so you have different overlays done, so you don't have to resample the data as you display it. And also important thing that now, for the time being, we are using those zip files, but zip format is completely not, does not allow for partial read. You have to access the entire file. Now there is a so-called SIG optimized zip. This is no new standard that allows you to stream only a part of the content. So just going through the examples, here you have the Copernicus Data Space browser. We will talk about it later also during our demo sessions, which allows you to search query. I hope you are familiar already with this. It's available for free. It allows you for 3D visualization, and of course in the background it does the data streaming. Another project that we had was with USPA, and it was in the framework of EU Space for Ukraine project, where we have created the WMST with Sentinel-2 cloud masking on the fly, as you can see. So here, WMST, it means that it's also temporal, so you can access multiple Sentinel images, and they will overlay over themselves. So if there is a cloud, for example, and on another image there is a cloudless image, then you will get, in the end, on-the-fly cloudless mosaic. You have the Sentinel Hub that have also a bunch of data streaming APIs based on the OGC standard. So this is a WMSE, WFSC, web coverage service as well. There are some proprietary APIs, statistical API, processing API, and you can also bring your own data to the Sentinel Hub. You can write such scripts that are allows you to, on the fly, modify the content of this data stream that you will get. And tomorrow at 3:30, we have a demo from zero to hero in half an hour, how to teach Earth observation coding for absolute beginners with the Copernicus Data Space Ecosystem. So if you would like to learn more about Sentinel Hub, please visit our demo. We have also OpenEO platform, which is also a processing engine with a very nice harmonized data access interface. So from the user perspective, you are focusing on the coding in Python, R or Java, and everything, the magic of resampling, data access, and in some kind, and also interpolation, it's done in the background on the server side. And as you can see, an example of such could be a crop type classification. There is also a very nice project by GeoVille called EarthStreamer, which is done in a framework of Dunia project sponsored by ESA, which aims at adopting Earth observation data in Africa, where you don't have good internet connections. So then the idea here is to convert the Sentinel-2 data for the time being to a kind of a movie format with compression, and also to take advantage of not only the spatial not only the compression in the spatial dimension, but also in the temporal dimension. So this is kind of a 3D compression, which is good for data cubes, for example. And this will be tested within the ESA Dunia project. For more, please ask our GeoVille colleagues. And I will end with this, with take-home messages. So basically, the data streaming has revolutionized a way that we access the multimedia. And now the same revolution is taking place for the big EO data. And what benefits that it brings to the user. So a user can obtain on-the-fly analysis-ready data over a specific AOI at specific time without the knowledge of the data format, calibration issues, compositing, reprojection, resampling, pre-processing, like cloud masking, everything is done on the server side. Thanks to this, users have more time for the real work, for the algorithm prototyping. Most of the data processing is moved from the client side to the server side, where the EO data repository is located. Thus, the user does not have to purchase costly computing infrastructure. And as we could hear on the previous presentation, the previous session, you're supposed to process the data where as close to the data as possible to avoid a large data movement and transfers. Streaming allows for massive computational parallelization and significantly reduces the input-output time. And this is also what we heard in the previous session regarding the Sentinel-1 and soil moisture. You can really access very small chunk of data, start to process it, and to get an output. And you can, using the REST queries, you can submit a lot of such requests in parallel. And just to finish, Copernicus Data Space Ecosystem offers for free up to some predefined quotas and advanced streaming protocols and APIs. And if you would like to learn more about those APIs, you can read the BiDS proceedings. You can visit us at the booth. There is also a documentation page. Tomorrow at 6 p.m. we have also a light bird of feather session when you can ask us directly about the question. And we have also demo session presentations. Okay, thank you.
Thank you very much, Jan. I'm afraid we don't have any time for questions, but as you said, there are plenty of opportunities to interact with you, to talk to you in the upcoming days, so please make use of that, and we'll just move on to the next speaker.
Okay, now we welcome Cesare Rossi to the stage, exploring the technological advances in EUMETSAT data store, data lake, and EUMETView. The floor is yours.
So, hello, Arnaud Carvenek from CS Group. So I'm going to speak to you about the work we are doing for data access.
Excuse me, I announced, I jumped in my line here. It's Arnaud, and it's multi-source, multi-domain data access with EODAG and EOCATALOGUE. My mistake, sorry.
Fine, no problem. So the work we do in that domain, and especially the work we do with two products we develop, which are called EODAG and EOCATALOGUE, which are two open source products to access multi-source and multi-domain data. So the current situation is that there is many providers. We list a few, both in Europe and wider scope, from different domains. So here we have Earth observation. We also have weather forecast, for example. And we want to access all of them. And when we do more advanced analysis, we want to access many of those data which are not available on on a given data source. Each of those data providers have different data discovery mechanism. We cited a few of them here. They have different protocols to access them, be it object storage, HTTP download, SFTP, and so on. They have different storage structure and compress, different type of compression, and they have different authentication mechanism. Meaning that if you need data set from 3, 4, 5 data source different, you need to know for each of those how to access them, how to programmatically access them to retrieve your data, which make it more complicated and more difficult to do. And in some time the way that you need to code to access the data, it becomes even a kind of vendor lock-in. So for that, we develop a library, a Python library, which is called EODAG. And basically what it abstracts to you, it's all the point I cited before. So it hides from you the protocols, the mechanism, and the discovery, and it translates everything into Python library, from where you can do your search and download your data. And then you have an extension to do, for example, some X-array optimization. And then a code looks like this in Python. So you say that you want to use the library. You declare it, you search for your product with some parameters, and then you are able to download it. And the good point is that you, in a configuration, you can specify what are the accounts that you have on each of the data provider, and it will look across to discover where the data is available and to retrieve from you, for you. And it means that you can do query with multiple data providers on the same way. Therefore, it removes a lot of the complexity. It's also available in CLI, and the same thing that in the Python library, but less pretty. We also have a Jupyter-like extension. So it's a plugin in your Jupyter where you can do simple research. You can see it. This is the product search you can have. So you can specify an area, a product you're interested in, date range, and some other standard parameters. And you can preview the result, and it makes you a list of all the products which are available. You can select one of them or multiple of them and automatically generate the code in your notebook. So again, the idea is really to speed up the access of the data. And as long as you configured your accounts on the different data providers, from your notebook, you can really query your data and build up a set of data from different type on a given area, for example. So EODAG, as again, it's open source, Apache2, available on GitHub. It's based on extension. So for example, we saw the Jupyter Lab extension. There is a EODAG Cube extension for X-array to make kind of data cubes. And each data provider is a plugin. So you can easily add a new data provider following the tutorial and documentation. EODAG have been used in many projects for BPE, ESA, European Commission, CNES, EUMETSAT. Yeah. So it's been quite useful, and we have make evolve the library based on the feedbacks we got from users. The limitation is it's related to your product and with weather climate forecast. As I say multiple times, you still need an account on each of the data provider, and you need one of each set environment. So what could we do to extend that beyond your product, beyond the server-side application, and also to remove the multiple restriction, because as we grow in the number of data providers, it's become more of an issue. And that's where we come up with EOCATALOGUE, which use a lot of EODAG server, and that solve most of those problems. And like this, you have a kind of a single account that allow you to access a lot of the data. And it provides to you a stack API as a norm with cross-collection capability. So you don't need to specify which is the product you are looking on. You can specify, for example, an area, and it's going to give you a lot of data. Again, it's open source Apache 2. Here it's the basic architecture where we use EODAG to connect to the different providers. We can either proxy it to the API, or we can reformatting, for example, if we want to change them into cogs as shown previously. We can also have harvesters that don't go through EODAG. That's, for example, things that we do for non-EO data. For example, we use Eurostat data that we change from an Excel spreadsheet to GeoJSON to make it as easy to use for the end users. So those are the ways that you can act. You can act it with static API, with a front end, and since it's also including EODAG, in EODAG, for example, using the Python library. Similar to EOCATALOGUE, EODAG, EOCATALOGUE works with plugin, and it benefits of all the improvement from EODAG. So each time a provider is added to EODAG, it's mechanically added to EOCATALOGUE. We can have reformatting plugin, and reformatting is quite vague in that sense. It can be, as I said, changing from Excel to JSON. It can be taking JPEG to COG, or it can be taking a COG to an ARD data. So it's really flexible. The idea is that you can prepare your data to make it easier to use for your end user. It will be available, so it's already in production, but we are cleaning things up to be published on GitHub by the end of the year. And it's used in Prometheus. It has been used for Airbus and the BPI, and it's a key component of the work we do on Destination Earth data lake with EUMETSAT. And if you have questions.
Okay. Thank you very much, Arnaud. We have plenty of time for questions. Sorry again for the confusion in the beginning. So, are there any questions in the room?
Hello.
Hello.
Louis, Teleservice Numérique. Very impressive, the work you did on EODAG. We use it a lot here. Just wondering, like, what is the business model behind it?
So basically, our business model is that we put it open source because we want to engage with the scientific community. And the same thing as EOCATALOGUE, it helps us to be faster to manipulate data for added value application. So for us, we see it as an investment to be faster, to reply, for example, for projects which are about AI application or analysis on a given area. And it has been quite successful in that aspect. The same for EOCATALOGUE, it helps us to have a pool of data which is wider, and we can do cross-domain application, mixing weather forecast, Earth observation, statistics from the government or the EU. We are currently adding data from biodiversity information, and we can combine them very efficiently. And like this, it helps us. It helps our scientific to not have to care about how we get the data; they just get it. And that's also something we want to bring to a wider community.
Thanks for an interesting presentation. I have a question. As your catalog is based on Stack, do you have any extension to this? like the ones that are common for remote sensing, for example?
Yes, so we just put stack, but there is a list of stack extensions which are compatible. And if you go on, if you have an instance of EOCATALOGUE, like for example the one from Destination Earth that we do with Cloudflare, you have the list of extension available. And when we put it open source, if it's open source, so if you want, you can contact us, but when it will be on GitHub, you can add extension if you wish. And in the same way that we interact with the community with EODAG, where we have contribution and merge request for EODAG, it will be the same case also for EOCATALOGUE. So and that would be the case for extension and so on.
Maybe I would have one regarding the EOCATALOGUE, actually two questions.
Yes.
Once it was written on the license, it expires 2023.
No, it doesn't expire 2023.
Okay.
It's Apache 2.0. It just right now we have tagged it Apache 2.0, and we deliver it to the EUMETView and EUMETSAT as Apache. It's just we are going to put it in GitHub end of 2023.
Okay, sorry.
So it will be publicly available for everyone easily by the end of 2023. The license will be Apache 2 for the coming future.
Okay, and a follow-up question: when you use EOCATALOGUE, can you also directly have the assets in the stack catalog, or are you just forwarding?
Yes.
Yeah.
So it's what I briefly showed on the architecture. You have a different mechanism. You can either have your own assets which are stored in the EOCATALOGUE. You can have derived assets. For example, if you choose to take like a JPEG into a COG, you can store it into an asset into the catalog. Or you can, and that's the main usage to avoid data duplication, federate a large source of data. The benefits of federating is that for a given data set, we can federate multiple data sources, which make it more reliable, and also sometimes it helps in terms of data coverage. For example, all providers do not keep 2 years or 3 years of data and just keep 1 year. You can mix and match between data providers, and it's done totally transparently by EOCATALOGUE.
Great, thank you. Okay, now we need to move to the next speaker.
Thank you.
So we're moving on to the fifth presentation in our session. Our presenter will be Cesare Rossi, and he will be exploring the technological advances in EUMETSAT data store, data lake, and EUMETView. Cesare, the floor is yours.
Thank you. So good evening, and thanks for joining this session. So let's start exploring what are the technological advances in EUMETSAT, in particular for 3 services that are data store, data lake, and EUMETView. I'm Cesare Rossi, a senior consultant in CGI, and for EUMETSAT, I act as a technical architect, and I follow all the design and implementation of these 3 systems that you see in here. I'm quite sure that the majority of you knows EUMETSAT. Here I just wanted to recap to highlight what was the problem at the beginning to solve. So first of all, EUMETSAT, as you know, manages the launches and operations of their own satellites, and then they are also responsible to disseminate the data to the general public. So they are responsible for the end-to-end. And then, more or less 6 years ago, it was clear that the generation systems that were available at that time weren't up to task in terms of performance, robustness, and most importantly, the access to the data. So what was established at that time was this program called Pathfinders. And these pathfinders, like the name suggests, is to find a path for the future, and in particular, a path to leverage as much as possible what the modern cloud architectures were available at that time. Read it as microservices architectures, for example. And on top of that, as the EUMETSAT owns also the hardware, there was an improvement on the available infrastructure and the systems, and all with the objective to have a system that is reliable, robust, and scalable, still reducing the total cost of ownership, tackling from different angles. What CGI did, starting from these pathfinders, was to support the client with a team of more than 10 people across different roles like developers, DevOps engineers, test engineers, architects like me, and also other partners. Here I mentioned Ask, GeoSolution, Conterra, 52 North, to help to develop these systems with in mind scalability, reliability, and self-healing, again, to reduce the total cost of ownership. Just a number here, currently these systems are serving more than 100 million of monthly API requests. So here, again, this is just to show how the systems evolved into operations. So started with the Pathfinders in 2017. Then in 2020, we had already the first system that went operational, which is EUMETView, which we will see in a moment. And in the same year, CGI won the contract to support the big data services. And the next year, we won the contract to support the big data visualization services, which EUMETView is part. And then the data store went operational in 2021. And this year, finally, the EUMETSAT data lake went operational in June. Without further ado, let's see what EUMETView is. So this is the web interface of EUMETView. As the name suggests, is to really visualize data. So it's providing the entire lifetime of the missions. Here, it's just an example of one so-called layer. Here, you, as a user, you can select many layers and then put them together, analyze, use some analytics functions. For example, here we are seeing the sea surface temperature, and for a given point, we want to know on a time period what is the temperature over time. This is just one example, so I will really suggest you to visit view.eumetats.int. It's self-registration, and you can play with that. There is one point that I wanted to mention, is this small icon in there related to the API access. So whatever is available in here is available through APIs that are OGC. So here, for example, there is WMS, there is WMTS for the temporal part. As you can see below in the line, there are all the acquisitions in time, and you can go back and forth and select your period for the analysis. So as a user, you could start this way. You start playing with the data, but then perhaps you want to go and access data. So you need the bytes. And then you go to data.eumetsat.int. This is the data store. So here you have data organized in collections. Here I'm showing the same one that we have seen in EUMETView. So here you want to access the individual product of the sea surface temperature acquisition. And you can do from the web interface, or again, with the same approach, we have the API access. So here we have OGC standards. There is open search for the search, and then you can access this data. Here I'm showing an example of one single product, and one interesting feature is the fact that you can access the individual files within a zip, within a product. And here the example is just one netCDF, but can be tens of them. And perhaps as a user, you want just to access one single, because for your analysis, it's the only thing that is needed. But if you're using the API, on top of that, you can use features of HTTP, like the range header, and you can access just the few bytes that you need, and you retrieve only the thing that you need for your analysis. And this is available, and this is operational. Some numbers from this year. So in terms of, on the left side, in terms of visualizations, it's 1 terabyte, almost 1 terabyte a day in terms of volumes of visualizations, and 1.67 millions of visualization a day. This is EUMETView. On the right side, we have the total number of users between EUMETView and DataStore. This is the average of users a day, and then the EUMETSAT delivered 4.15 petabytes only this year of pure data access. I didn't mention data lakes so far, because data lake is not directly accessible from the users, but you can see it as the back end of the data store. So the data lake is the system on the bottom part of this, let's say, simplified architecture of the system. It's for the internal users plus for the external users through the data store. The architecture is a little bit more complicated than that, but I wanted just to highlight a couple of improvements that we are doing right now. One is low level. What we are doing is analyzing the performance of a single HTTP request that flows into the system. There are many points that are touched at network level, so we are working by improving the single request, because we believe that if we do that, then the overall throughput will be benefit. On the other side, we are evolving these systems, and in particular, there is an interesting feature that will come very soon, that is the notification for the users using some kind of modern protocols that I will not mention now because it's under development, but you can expect in the coming year that there will be a new system to get notified when new data comes using modern protocols. This is for EUMETView. We'll be quick on that. What we are doing, what we did is that on the server side, we have GeoServer and we have Postgre. We work to scale Postgres, having a single master, multi-slaves architecture. And on the other side, with the help with our colleagues from GeoSolutions. On the other side, in the image generation service, so the service that prepares the visualizations, we are evolving it using modern workflow implementations using open source and open source library like SatPy, because the idea is that this is then an improvement is given back to the open source, and an improvement from the open source community will be then incorporated into these kind of systems. This is just an overview of the technologies. In case you are interested, we are at booth 8, so if you want to speak about that. And that's it. Thanks for your time.
Thank you very much, Cesare. We have time for a few questions. Are there any questions out there?
Maybe one question regarding the metadata and the APIs there. We heard a lot about Stack today already. Is this something that you also envision to add to your service at some point?
There is some discussion in this regard for Stack. Nothing yet planned, but yeah, there is a discussion ongoing.
Thank you. Any questions from the audience at this point? Well, there's going to be plenty of opportunity to talk to you during these days. So thank you very much, Cesare.
Thank you.
Thank you.
Okay, then we come to our last speaker of today, which is Martin Sudmann, and he will talk about how green is Austria, an Austrian-wide information layer based on semantic querying of EO data. The floor is yours, Martin.
Thank you, Alex, for the introduction. Hello, everyone. Thanks for staying to the last session and the last talk of today. The context of my talk is I will present an approach that we use to create Austrian-wide information layers based on a technology that we developed. That's called Semantic Earth Observation Data Cube, and I will explain what this is. So that's just the context. This is a data cube. I assume that most of you will know what a data cube is. Typically there's the reflectance values in there. Let's look into one cell. What we do in addition is that we have categorical variables. So each of the spectral signatures will be assigned to a spectral category. And this gives a couple of advantages. So it looks like a small step, but it's actually a big advantage because the data cube knows what it contains. So the semantic is there. In addition, we derive some additional continuous variables about brightness or greenness and so on from the measurements. And then obviously we have some additional geographic variables, altitude and exposition and so on from the tail elevation model. So this is a semantic Earth observation data cube. And if this is instantiated somewhere, then you can use any of these information or data that you see here to create a semantic query and actually derive the information that you want. Let's have a look at the categorical variables that's shown here, how we derive them. In general, there's a lot of options to do that. We use one option which is called SCIEN. This is a software toolbox which is fully automated and based on a physical model, so it does not need any training samples, but it works worldwide. It's very fast and scalable. Maybe in this session, what is quite interesting is that it also supports multiple sensors. So you can derive the same categories from different sensors, Landsat, Sentinel-2, and so on. And then on this semantic level, you can compare it and you can involve them into the same query. So this is an example how the categories looks like that we derive, and you will see this is not land cover, it's below land cover, but it's actually an advantage because it's very generic, it's not specific to a particular application that you want. The application comes on top of that. So once you derive the semantic categories or the spectral categories, then you can use them and you can extend and you can create your own land cover on the fly that you want to derive, or in our case, some information about the vegetation status. This is applied to all images and then stored in a data cube for make them queryable. So this is an example how this will look like. Maybe you see the smaller variations in the watercolors and the vegetation and so on. And if it goes through our process, it looks like this. So each pixel knows whether it's vegetation or water and so on. It's not, if you look at these areas, it's not, doesn't tell us that this is a forest, but it tells us this is a strong vegetation or weak vegetation or these type of things. And then obviously in a data cube, we have all these categories available, and then we can start querying them. So it's basically stacked upon each other, and then based on the categories, so on the sequence of the categories, we derive some information, whatever this is. In this case, this is a simple count, so just counting over time how often the category was seen, and this can be done with any categories. You can exclude categories, you can include categories, you can use different reducers, and so on. So what's in the semantic queries? You have your categories of interest. In our case, it is mainly vegetation. You define your area of interest and the time that you want to apply this to, and then you submit it to the data cube, and then it will be executed and you get the result. How you do that is you have two options. Either you can write code. You can also do this in a graphical way. So we have this graphical interface where you can just drag and drop your query into this semantic model, and then it will be automatically executed in the data cube. The inference engine that's doing this is called SEMANTIC, and it's open source. If you want to have a look, just go through this website. So this is an example. What we derive in this case, what I want to present is actually 3 + 2 information layers. The one is vegetation percentage, then the maximum greenness, the standard deviation of the greenness. And then in addition, the quality information, like how many observations were in there, how many valid observations about cloud and snow and so on, that you get an idea not only about there was 40% vegetation, but also what other categories are in there and what is potentially distracting from it. And these information layers will be free to use. So we are currently working in a process to publish them as a stack catalog. Okay, so this is an example how this will look like for Austria, the vegetation percentage, and then you already see the different land covers, like the forest. You see the big cities, infrastructures, water areas, and also the higher mountains, which obviously don't have any vegetation. Then we have the maximum greenness. So this is a map that shows the maximum of the greenness value that has been observed. And you see it looks a bit similar, but you see also quite some differences. And this is more emphasized on this slide, which I want to show. So on the left side, you see the maximum of the greenness, and then you see the percentage of the vegetation on the right side. So you see that, for example, in alpine pasture or in agricultural grassland, you have a high maximum of vegetation throughout the year, for example, but the duration maybe not as long as, for example, in a forest area and in other areas. So these 2 layers you should basically combine and use them together. Then we have the standard deviation, and this gives us some information about the fluctuation, let's say, of the greenness. What's the difference between the minimum and the maximum, and so on. So these 3 layers are intermediate semantic layers. You can look at them; they are nice, but you should also use them. And this is basically one of the core messages that we create these semantic intermediate layers, which are supposed to be used in further applications. So how can you use that? For example, you can simply create nicer maps or more expressive maps. Let's say if you just have the greenness overlaying on top of some other data sets or other maps. You can use the data set, combine it with other data sets like agricultural field parcels or permanent settlement areas, forest areas, and so on, and then further process these data. What we did in this case, as an example, is we calculated this for several years and then identify for, in this case, the build-up areas, the time of the construction building, or exactly more precise, the time of the vegetation removal. And then you see also this is the same area. You have different times or different years when the vegetation was removed, color-coded in this cube. So there are several potential applications where this can be used. You can identify green areas in city. You can identify permanent vegetation removal. You can support SDG-related indicators. We derived the mountain green cover index, for example. Many more things. What I want to say is it is supposed to be used in combination with other data sets. Maybe also able to find some errors in other data sets with that. But the main message, and I want to close my talk with this, the main message is it's important to have these kind of semantic layers on several steps, let's say, in the data cube itself, but also then on these derived information layers where you can build your application step by step. This was all about my talk. I appreciate that you stayed to the last presentation. I also see still some happy faces after my presentation. It's good, so we're prepared for the group picture, I guess. Thank you very much.
Thank you very much for your talk, Martin. Also, very nice updated visualizations. Good job there. Are there any questions here in the room? I see one already there in the end.
Yeah, thank you very much for the very interesting talk. Could you elaborate a bit more on the difference between your categories and land use land cover?
Yes. So our categories are a category of the spectral signature. So it does not tell you what land cover it is, because several land cover units may generate the same reflectance, and you need some additional information to derive that. You can include the space or time and so on. But here, this is really only based on the spectral signature, and therefore it is very generic, telling you that it is, for example, strong vegetation or weak vegetation. It does not tell you that it is agricultural area or forest. This you can derive by semantic querying using these categories. For example, if you observe that vegetation categories are disappearing, then bare soil categories are appearing, and then vegetation categories are appearing again, then this is an indicator that this is a certain type of agricultural land. And then if you know the time, then you can go further. Most land covers are going directly from the reflectance to the land cover unit, and then therefore only applicable for this specific application that's supported by the land cover, by the entities of the land cover legend. And if it's not supporting your application, you need to go through another land cover map. In this case, you have the spectral categories as a building block, and you derive your land cover on top of that on demand.
Thanks. We had another question over there.
Yeah, thank you for the interesting presentation, Martin. Just for my understanding, so it's based on the CM software, which is able to extract this information on Sentinel-2, am I right?
So we use the software, but you can also use other tools as well.
Yeah, of course, because you can
Yes.
also include, as you mentioned in the end, a kind of SDG indicators rather than other type of activities. But the question actually is, so the possibility to perform this type of, let's say, cross-query in time, space, and, let's say, value, no? Are you enabling also this via user interface or also only via API?
Yes, so good question, thank you. We have two options. So you can use the API of this Python package, SEMANTIC, or you can also use the graphical user interface. So you can use both. And for the first part of the question, I actually have a poster afterwards where we use the same approach to the Google Dynamic World dataset, which have also not spectral categories, but land cover classes in this case. But also there you can query them through time and space. So this concept is more generic, but we use the SIAM software because it's the one that works best for us. Thank you.
Okay. Any last question in the room? Yeah, there's one from Daniel. Go ahead.
Yeah, also thanks for this very nice talk. Understanding question, is these semantic data cubes, are they basically multi-dimensional data cubes, or is there some difference? Because in the end, these layers you could also just put in an extra dimension, right?
Yes, so they are multi-dimensional, and so at least they have space and time and thematic. And then during the query phase, which is not shown anymore, but during the query phase, you can create as many dimensions as you want, as long as you keep track of that. But the system gives you a lot of options to add as many dimensions as you want.
Thank you. Okay, we need to come to an end here. So thanks again to Martin.